I want to now do a couple of special cases, and then we can take a break before we go to the second half. The first special case is the simplest possible special case. I want to consider what happens when you have n identically sized positions across your assets. So in other words, equal weighting across the n assets. That's an example of a perfectly legitimate portfolio. Not a very smart portfolio, but a simple one. So if I have an equal weighted portfolio of all my assets, my portfolio weight is 1 over n. So when I plug that into the formula, I get a very nice expression for the variance of my portfolio. The variance of my portfolio is the average variance of my individual securities divided by n. And then it's n minus 1 divided by n times the average covariance. When I let n get big, when I let it go to infinity, it turns out that this first term disappears. And what I'm left with is the risk of your portfolio is going to be given by the average covariance. It has nothing to do with the risk of any individual investment. It has everything to do with how related one investment is to another. So thinking about correlation is obviously central, and this is a very simple illustration of it. I want to give you a second illustration, though, a second example that will give you a sense of where hedge fund managers are coming from and why they get so excited when they are able to find assets that have low correlation to existing portfolios. So to do that, I need to do a little bit more work. And the work that I'm going to do has to do with calculating the variance of a particular portfolio. So remember that I showed you the expression for the variance of a portfolio as variance of the return of a portfolio is going to be given by the portfolio weight times this sigma matrix times the portfolio weight again, this quadratic form. So I want to consider an example where I've got a portfolio of n assets that have the same pairwise correlation with each other. So any I and j are going to have the same correlation row. Okay? And this is what the matrix looks like. This is the covariance matrix. So I've got to start with the correlation matrix and multiply by the individual standard deviations, sigma. And since I'm assuming that the assets have the same level of standard deviation, sigma times sigma is just sigma squared. So when I multiply sigma squared times this funny looking matrix, I'm getting my covariance matrix of a set of assets that have identical pairwise correlation. Okay? Now, it turns out that this doesn't allow me to assume any arbitrary correlation. The correlation has to satisfy this inequality. Otherwise, this matrix is not going to be a bona fide covariance matrix. It'll give us weird answers like negative variances, which we know we can't have. So given this matrix, I can calculate the Sharpe ratio of my portfolio. And the Sharpe ratio of my portfolio has a really interesting and simple expression. It's equal to the Sharpe ratio of each asset individually multiplied by this multiplier. And the multiplier is a function of just two things, the number of assets and the correlation. And so I'm going to just plug this in for you now. I'm going to just focus on the particular multiplier. I'm not going to worry about the individual Sharpe ratio for individual assets. I want to just focus on the multiplier. And here's what the multiplier looks like for various different values of rho and n. So let's just do one example. Suppose that the correlation among assets is 90%. So you got a bunch of very, very highly correlated, very similar assets. Okay? Notice that as you increase the number of assets in your portfolio, if they all have very, very high correlation, the multiplier doesn't really go very far from 1. You're not really doing yourself a big favor in boosting your Sharpe ratio by adding lots and lots of assets that have very high correlation. But what if the correlation is like 0.4? Remember that McDonald's and Pfizer rather was correlated at 44%. So what if the correlation were 40% and we added more and more assets? Well, look, the multiplier goes from 1 to 1.2 to 1.5 all the way up to something like 1.58 as a kind of a limit. So in other words, if you could actually put portfolio of assets that have correlation of 40%, you can boost your Sharpe ratio by as much as 58%. You can increase your Sharpe ratio by as much as 58%. Okay? And now I want to show you the most interesting result, which is the orange row. The orange row is where there's no correlation. If there's no correlation, then the more assets you add, the higher the multiple goes. And there's actually no limit on the multiple. The sky's the limit. In other words, if you added 100 assets that have no correlation, you will multiply your Sharpe ratio by a factor of 10. That's extraordinary. Think about that. So if I have lots of assets that have no correlation with each other, I'm getting huge amounts of diversification. And I can boost my Sharpe ratio to almost anything, anything. Right? I have to find the assets, of course. I may not be able to, but if I can, this tells me that there's real value to be added. In a way, this is almost an arbitrage opportunity. It's not actually an arbitrage, but people call it a statistical arbitrage. I'll come back to that a little bit later on. So that's the basics of mean variance analysis that we need. And before I apply this now to orphan disease portfolio, we're going to actually have to apply it to capital budgeting. In order to do these calculations, in order to construct the portfolios, you need the covariance matrix. You need sigma. So how do you get sigma? Well, one way, a common way, is to calculate it using historical data. But as you will find out tonight, and as you work on problem set 4, historical data is not always an accurate guide because things change over time. And so historical data is the starting point. It's not the end point. So you start with that, and you calculate the covariance matrix, and then you look at it, and then you say, that makes no sense. That can't be right. I need to change it. So you then need to add on top of that judgment about what the correlations should be. So what I mean by judgment is making use of the underlying mechanisms of the correlations. If you were an equity analyst trying to look at McDonald's versus Pfizer, and you calculated 44%, you would actually dig into the cash flows, dig into the customer bases, dig into the businesses, and look to see whether or not there are any particular circumstances that would cause you to adjust that 44%. For example, suppose it turns out that McDonald's happens to have a division that's concerned about the health impact of its food on the population and realizes that cholesterol is a pretty significant issue, and maybe they ought to develop some kind of an anti-cholesterol therapy as part of the McDonald's offering. You get a Big Mac, and then you get some PCSK9 medication to take cholesterol out of your blood system. If they did that, if they announced that, what do you think the correlation should be between Merck and McDonald's? Up or down? Up or down? If McDonald's gets into the drug development business, you would think it would go up a little bit, right? It turns out that by looking at the nature of the businesses, you can actually often say things that are forward-looking rather than rearward-looking. In the case of orphan diseases, which we're going to take up after the break, that's a situation where the biology tells you something about the correlations. And you don't need to go back and look at historical data. In fact, I would argue that historical data can be misleading because it doesn't necessarily take into account some of the biology of these orphan diseases. So that's where using scientific insights mixed with financial insights will give you opportunities that you wouldn't ever be able to have with either one or the other. You really need to mix the two in order to be able to see how to make the best use of these tools.